In this talk on equatorial wave current interactions, I will, okay, the talk is first based on joint works with Adrian Constantin and Colin Martin, so it's based on mostly on these two papers of ours. So we consider a framework of two-dimensional equatorial flows in the F-plane with no meridional variation. So essentially, sorry?
F vanishes on the equation. F vanishes on the equation, it's beta plane?
Okay, I'll explain later, probably. It's with no meridian. It's in XZ plane. So if y is over the meridian, so z is the vertical variable, okay, and x is east-west, y is north-south. So there is no y variation. So it's in XZ plane. So on the equator.
Yeah. Plane in which f is constant.
Okay, let's.
F is constant. You mean something else?
Yeah, probably I mean something else. So okay, forget about this. So I will explain in details what's going on, and then. We will make a certain representation of the velocity flow, some assumptions that the velocity flow will be a perturbation of the average current with something that's actually potential, with potential part. Our main idea is to represent the equations in Hamiltonian form and then to work out various approximations. So this is actually what the picture that we have in mind. So as we said that this is, Z is the vertical, well, here it's Y, but it's actually Z. So we have an internal wave. So this is a system with two densities, and it involves surface wave, which is at some level, on some average level, H1. And 0 is the average level for the internal wave. So this is a domain D1, this domain D2. So we have approximation of a flat bottom here. Flat bottom, and here we have some internal wave that propagates with two densities ρ1 and ρ bigger than ρ1. And we have also an average profile for the underlying, for the shear current. That's, well, we take a piecewise linear approximation. So we have here current that, because the winds are blowing in the west direction, and we have equatorial undercurrent in this direction. And we have vorticity gamma 1 here, which is negative. That's due to the shear current, and here some positive vorticity gamma. So we have this configuration set. This is the.
Just before I'm totally lost. Why is directed northward or upward?
Huh? Z.
Why? Which way is y?
There, y is the variable that is north-south. So there is no y variation. So this is at the equator. No, this is wrong. So this is z. So. So because we have no y, but this is in some other, okay, don't mind that. So we have currents with constant vorticities and internal waves that are coupled with surface waves, and the notation is the surface wave plus eta 1 is the elevation of the surface wave, and this is just eta of the internal wave. Okay. So the two domains is the domain of above the thermocline or pycnocline, which is here, it's D1, and this is just D, sorry, this is just D. And here, the quantities here, they have subindex 1, and here they don't have any subindices. So we have densities like this, and the here the velocity field is with components U1, where we should write 0, but because it's two-dimensional and W1, and here is U, and W is the first and the third components, yeah, only. So essentially. And then we can, of course, write the governing equations with the Coriolis force term included, gravity and Coriolis force. So we know that the Coriolis force basically pushes the motion that's in the north hemisphere, it pushes it south, and vice versa. So it's kind of acts more or less like a waveguard that pushes all waves to guides them towards the equator. So we are actually not considering north-south, the meridional variations, only concentrate on our attention on this two-dimensional picture. So in 2 dimensions, the Coriolis force can be written in this thing where this is the rotational speed, and psi is the stream function of the fluid. So essentially, we have 2 fluid domains, and in D1, we have Euler's equations in this form, and in D, so here in this, we have another set of equations where this is the rotational speed, and we represent the 2 densities like this. For example, ρ1 here is the density of the fresh water. That's, okay, probably you will correct me, but it's the lighter than this is the salty water below the thermocline, which is explained with this parameter r. This is ρ1 times 1 plus r, where r is the factor that's... And of course, we have mass conservation in these 2 fluid domains. And as I said, I have mentioned before on this constant vorticity distributions. So we have to also add the boundary conditions for atmospheric pressure on the surface. So this is the kinematic boundary condition on the surface. We have 2 kinematic boundary conditions from up and down on here on the thermocline or on the interface. And we have equality of the pressures below and above the thermocline. So we also assume tangential velocity balance here on the interface. So the interface here is z equals eta xt. And this means that, okay, because our flow is not viscous, there is no viscosity, so I mean, there is no problem to have, to have some tangential difference. But on the other hand, on the other side, there is always some viscosity, and any tangential difference might be able to destroy the thermocline. So for consistency, for consistency, we take this as well. Okay? And then the currents, where gamma h is the average current here on the thermocline. So we have these linear expressions. And okay, for what follows, we go for some this non-dimensional exercise. So where we are going to pick up a scale, say 500 meters, and velocity is, say, 0.5 meters per second, because for our main attention is on the internal wave, and there the sizes, the typical sizes and velocities are of this range. So if we go and make this non-dimensional thing, non-dimensional exercise, so the letters with a bar are the the quantities that have the dimension. Sorry?
So it's a large Rossen number you choose?
No, we don't actually.
What's the number of the 7?
Uh,
What's 7? Your fruit? G is your fruit number?
no, G is the Earth acceleration. So the non-dimensional exercise for the Earth acceleration in this scale, if we put up this scale, so G bar is the usual 9.8. So, but with the non-dimensional G is 2 times 10 power of 4. So this is the non-dimensional G. So this is kind of the non-dimensional rotation. That's 0. It's quite small. So here we have the other things, the pressure and so on.
But your L is just you're picking it from the.
Yeah, we pick up we fix a scale. That's, for example, the phenomena that we consider. For example, we take this. We can take something else, but this is kind of 500 meters.
What's the importance of 500 meters?
So these are this is something like a scale that's relevant for the phenomena that we are considering.
But in the setup, you have 500 meters anywhere, like the top layer is 500 meters thick or something?
Actually, say, typical vorticity values will be like this. Typical top layer, something like 120 meters, and depth 4 kilometers, so the non-dimensional values are this. Well, it is just that the scale that we can fix a priori. So this is to do with we can think that this is something like the length scale of the wavelength of the waves that we consider, for example. Or the size of the horizontal sizes of the structures that we have. It could be the wavelength, could be these things. So, and then we can write the equations in this. They look the same in more or less with this. We just replace with the non-dimensional things. But the next assumption that we make is that the velocity field can be expressed as a perturbation of the current field plus something that's potential, so that the wave motion is essentially encoded in this potential part. So psi1 are of course the stream functions, but we have phi1 that are some potentials associated with the wave motion. And these are the vertical velocities. So with these assumptions, we can, for example, integrate and write formally the expressions for the psi1, the stream functions in the 2 domains. And it's written in such a way that we have this one that, okay, first of all, if z equals minus h here at the bottom, we start from here, the bottom stream function 0, and in a continuous way, the function is from here, say, psi to psi 1. Okay. Psi can be continued in a actually continuously differentiable way, but not twice continuously differentiable from here, from the lower level to the upper level. So given that the velocity field has satisfies some how to say, some reasonable conditions, like they are precisely given in the paper, something like Lipschitz continuous everywhere. So the stream function in this way can be continuously, and of course it satisfies this with the constant vorticities. And then we consider essentially solitary waves. So for this and we want this eta and eta 1 to attenuate at infinity, and the corresponding potential as well. Actually, we will need more later on, because we will be considering various operators. We will need these functions to be smooth enough. For example, Schwarz class. For phi and phi 1, however, we have to say that under these conditions, phi extends C1 to the closure of the domain, but phi does not extend in a continuous way to phi 1. So in a contrast to the psi, in this way.
Is that potential shift between the stream functions?
No, this is phi.
The second one.
Yeah, this is phi. Yeah, phi and phi 1. And with all these assumptions, we write the kinematic boundary conditions with all these potentials and Euler's equations in the two domains. And what we can do is, okay, for example, at the surface, we can integrate, okay, we can, we can integrate somehow these using the conditions that we have imposed on psi, because psi appears here. So from here we get this one, and for the domain D1, here are some constants that depend on the constants of the problem. Similarly, we can, this Nabla operator, we have another set of constants, and from these two equations, we, given that on the surface we have the atmospheric pressure, so here we have P equals P1 from equality below and on the two sides of the thermocline on the interface, we obtain the Bernoulli conditions, like this is on the surface, Z is H1 plus eta 1 here on the surface, and chi1 is actually psi on the surface. So here we have another Bernoulli equation where chi is psi at the interface. So these two actually are, for a continuity, they are two stream functions are equal here. So we have, okay, so the problem is such that if we know the motion on the surface and the interface, on the bottom, of course, we don't have vertical motion, we can, from analyticity, we can extend here in the bulk of the fluid. So all the information is actually encoded in these variables on the surface, the potentials on the surface and the elevations eta 1, and somehow the combination here, phi 1, and from the second Bernoulli condition, it's some sort of combinations of this phi and phi 1 at the interface, so that has subindex S. So our hope is that we should be able to consider these eta and eta 1 as kind of generalized coordinates in an eventual Hamiltonian formulation, and we will need to find what are their conjugate momenta, and it seems that there's something like these guys, phi 1 and phi, and their combinations on the surface and the interface. So the Hamiltonian formulation is we have to look at the Hamiltonian function, and this usually comes from the energy. So the energy this should have been actually W1 because I have introduced here W1, is the kinetic plus potential. Yeah, sorry, this is Y is Z, yeah. Sorry, so it's a mistake, yeah, Y is Z, yeah. So this is a general, the kinetic energy is just the kinetic energy and the potential energy, the entire fluid, but it will be infinite because we have a flow, and the energy of the flow has to be extracted. So it's actually a very long and painful calculation, but eventually we can arrive at the following result. So the proper variables are phi 1, let's say that this is the trace of phi, the interface, this is the trace of phi 1 on the interface, and this is the trace of phi 2 is the surface. So if we define this variable, that's combination of phi and phi 1 on the surface, and that their difference, and this other variable that is just phi. So this is on the interface, and this is at the surface. So these are candidates for a conjugate momenta that correspond to the coordinates eta and eta 1. So it would be good if we can express the energy, minus this infinite energy that's on the current, of course, because it's infinite but constant. So it will be good if we can express somehow the energy of this wave motion with only these variables that are defined on the surface and on the interface. And as a matter of fact, we can do it, but we need, we can have a formal expression, but we need this to use these Dirichlet-Neumann operators that they have complicated definition, and they are related to this potential phi and phi 1. For phi, it's the definition is like this, and for phi 1, it's we have two surfaces. It's between the surface eta 1 and eta, so it depends on two. The layer depends on two boundaries. So we have actually this more complicated definition that results into a matrix form of the Dirichlet-Neumann. And if we introduce this other operator B, that is 1 plus R times G on 1, we have a full set of Dirichlet-Neumann operators. Well, there are perturbative techniques for their computation. There are even numerical techniques for computation of these Dirichlet-Neumann operators. Of course, the computations, they take space and time, but to make the long story short, this is the Hamiltonian written in terms of these variables, Hamiltonian variables, and in terms of also these Dirichlet-Neumann operators that so far we don't know what they are, but we have, and we have various constants here that are related to the constants of, the physical constants of related to our system. So it's quite a cumbersome expression. But moreover, so this is only the energy. We don't even know that if this is the Hamiltonian. So with some more efforts, we can write the equations that I have mentioned before, the Bernoulli and the kinematic, all these equations that on the surface and the interface, we can write them also in this form. That's, mu and mu1 are constants. If we ignore these things that are related to the current, we have here something that looks very much like a Hamiltonian system, a canonical Hamiltonian system. But these two things, they make it non-canonical somehow. Maybe not even Hamiltonian. But luckily, if with a little bit of change of variables from psi to zeta, so these terms can be absorbed, and the system can be actually written in a proper canonical Hamiltonian form in terms of these variables. So it's actually even with two layers. So this extends Zaharov's results, I should have probably mentioned. Zaharov did it for his classical paper from 1968. So now this actually for two layers, and probably it's going to work for more. It's only the Dirichlet-Neumann operators will be awfully complicated if we go further and expand. But what are these Dirichlet-Neumann operators? I mean, before that, I have to, again, what I mentioned before, that for these variables, eta, psi, and zeta, we should, considering solitary waves that attenuate at infinity and are smooth enough in Schwarz class, then we can make sense of all these expressions of the Dirichlet-Neumann operators and the corresponding variations and so on. Okay, so now if we want to see, for example, what is going on, let's take a small parameter that's A is something like the amplitude of eta and eta1, and let's think for the moment that eta1 are the same, although they're probably not, scale, and we can expand this the energy, which is the Hamiltonian. And quadratic, of course, H2 will produce, of course, the linearized equation. So the linear equation, because its variation is from quadratic, it produces linear equations. And I'll give you just a flavor of what it is. If D is this minus IDX, an operator like this, K is the, let's say, the wave number, that's 2 pi over lambda. So D acting on a basis like this, IKX, is just multiplication by K. So this is, I mean, expanding the Dirichlet-Neumann and so on and so forth. This is the kind of equations that we linearize that we have for psi and eta, and another for psi1, eta1. So this is a system of linear, but they are quite complicated system of four equations. So, of course, with the Fourier transform, where k is, this operator D is just multiplication by k in the Fourier space, we can write it in this form. Where M is a matrix, U is the column of the unknown variables. And the eigenvalues of this matrix M are associated to oscillatory solutions of this form, IKX minus CT. Yeah. So eventually, zeta or zeta, the solutions will have this form where eta 0 and psi 0, they are, I mean, if t equals 0, they are related to the initial profile. And same for eta 1. So we have this and this. Okay. What we have from this system, when the t derivative is actually minus ikc derivative, and when we put all this in the system, we have a determinant. We have fourth order homogeneous algebraic equation, which is consistent only if some 4x4 determinant is equal 0. So we have a complicated equation for this the dispersion relation. So it's a polynomial of degree 4 with coefficients that depend heavily on k. And we did a bit of an analysis there about looking at this dispersion relation. And okay, briefly, the result of this analysis is the following. That the matrix M has four, I mean, K is the non-dimensional for a very large range for wave numbers between 0 and 64. M has four distinct, purely imaginary eigenvalues. So we have four real propagation velocities for a range of basically this covers probably most of the physically.
So these are presumably are related to some known waves?
Yeah.
So which waves are they?
Yeah, I will make a comment about. So the linear, okay, so the first thing is that the linearized problem doesn't admit solitary wave solutions. They are only periodic, I mean, and this is something to be expected of oscillatory solutions. The next one, okay, so here it is. So the short waves, first on the short waves is for large values of K. We have approximately, so this is an approximation, C plus minus, we have traveling wave that's this one has no effect basically on a thermocline. It's a kind of a surface wave. So physically it's 12 meters and minus 13 meters, something like this per second. And here we have on the internal wave, we have short waves that are of this magnitude, 1 and 0.72 meters per second. But this is in short wave. So what's more interesting, and this probably I don't even know if they can be detected or. So what's more important is the long waves. So the long waves, they correspond, say, K less than 0.2. We have, this is obviously the current plus minus the very well-known formula for the surface waves, left and right, plus current, that are something like 2 plus minus 200 meters per second. And we have also another pair of values which corresponds to the measurable speed of the internal waves that are approximately 1 and 1.5 and minus 1 meters per second. Yeah.
Before you do the short waves, what happens for K greater than 64? They're unstable?
So K bigger than 64 would be probably beyond any thinkable physical range because the.
30 kilometers.
But this is non-dimensional K. Let's be.
Non-dimensional is on L, which was 500 meters.
Yeah.
So it's only.
No, I have
it's
to.
only wavelength of about 30 kilometers. Ocean, that's not huge.
Probably there are other things, but I mean, okay, so the.
But your analysis is saying there is instability there, presumably, because there you don't have the idea that four imaginary roots, you now have some real roots, which means that there are instabilities. Does that mean your basic problems ill those in some way for describing what you want to describe? You can't just throw out the short wave.
So we're not throwing out the, well, we have seen that.
This also for K greater than 64.
Okay, so this is probably a good question, so that cannot answer immediately. But because our main idea was to look at mostly at the long waves, because they are something that's more spectacular in these things. Yeah. And yeah, these are, and what's interesting that this C3 and C34, they kind of approximately coincide with the characteristic speed that one can get from the rigid lead approximation. So because this one can be tackled also if one thinks that this is a rigid, like something like a bottom. So in most papers, in some papers the approximation of the surface is just a rigid lead without any variation. So. And the other two routes, they kind of approximately coincide with the analysis of this rigid lid approximation. And now, the rigid lid, for example, we have done this with Tao and Compeli and myself in Journal of Mathematical Fluid Mechanics. Okay, but now let's go to look at weakly nonlinear approximation. So you remember these things. Psi x, or the potential, this potential variable, that's generalized momentum. Psi x is something like some sort of velocity. So this is a bunch of constants that we need, and this zeta and zeta 1 are the canonical variables. So it's actually would be better if we hit them by x derivative and introduce q and q1 related to these old variables, and then the Hamiltonian structure has this, the canonical structure in terms of the new variables, it has this form. Now, again, let's look at some scales. For example, distances, let's introduce parameter epsilon, that's not the previous epsilon, less than 1, such that our physical distances are, say, L over epsilon. So for distances much bigger than L in propagation. And then this, again, is some scaling for eta and eta 1, where the prime variables are order 1, and these are the non-dimensional but unscaled variables. And the scaling is so that the velocities here, dt eta and dt eta 1, of the same order. And if we looked at the Hamiltonian and expanded, if delta, okay, delta is another one that we are going to specify later on, but of order or epsilon or smaller, and if we work out the expansion again of h in terms of these canonical variables, up to epsilon 5 or epsilon cube delta square, we have this Hamiltonian, and some other constants, we have a system of coupled equations. So these are on the surface, and another one on the thermocline or pycnocline. So it's a complicated system that also depends on the scales and everything else. But, okay, so here we see that we can, if the scale delta is much smaller than epsilon squared, we can decouple the equations in such a way that the elevation here on the surfaces entirely follows the motion on the thermocline, and then these two equations, they are kind of coupled equation for the motion of the thermocline. So this is what we have. And then we also see that this is conserved, and yeah, the equations on the thermocline in the leading order, they give us this propagation speed, the linear, doesn't depend on k. So we have two left and right running wave. Again, what's interesting that in this case, this is not they're not the same as the rigid lid, although these are really small. So the rigid lid and small variations on the surface which follow the waves on the thermocline, they're not the same. And this is actually true. This has been noticed in the works of Craig. I should have mentioned that Walter, Craig, and Coulters, they did a lot of work on this in the irrotational case, on the Dirichlet-Neumann operators and related stuff. So even in the irrotational case, these two characteristic speeds are not do not coincide the expressions with the rigid lid for some reason. So it's seems that it's fundamentally different if we have small but non-zero waves that follow up here, or if we have just a rigid lid situation. Okay, so because this term is really small, these are real as we should have expected. So the plus minus is for left-right running wave. So this is what we have for the zero vorticity case. And if we introduce C0, this is minus the current, and C1 like this. So in the leading order, we can have Q as well. It follows, it's proportional to eta from the linearized equations. So we can, going further, in the expansion in terms of epsilon, we can expect that there are some more terms of this form following the idea of Robin Johnson. So in some papers, they call it Johnson's transformation. And with this one, if we exclude Q from the system of the two coupled equations, we will get two equations. They have to be the same. So B1, B2 are some yet unknown constants, but from the condition that the two equations, they have to collapse and produce one, say for eta, we can actually determine these two constants. This is Johnson's idea. And then the result is that eta1 and q1, they follow these are the unscaled one, but the scale is epsilon squared. That's not written here. The variables on the surface follow the variables, eta1 follows eta. And their ratio, it seems that it's positive for, at least for the right running wave, and probably for the left running wave also, unless there are some pathological values of the parameters. And these are comparing the equations, we have expression for the two constants B1, the unknown, and constants B1 and B2, and ultimately the KdV approximation. So here with coefficients that depend on the constants of the problem. So the KdV is the best probably studied system, integrable system. So the inverse scattering, the soliton solutions, and everything is extremely well studied. So this actually would indicate that we expect here solitary waves. And the signs of these coefficients, they would determine if these are the waves of kind of solitons like this or solitons of depression. But nevertheless, this indicates the existence of solitary waves over the thermocline. And indeed, there are some, this is something that one can observe. So there are some pictures from the Andaman Sea in the Indian Ocean. It's not quite equatorial. So it is, but it is somewhere, the depth of, so there is a flat part of the bottom with this size. And there are some pictures that are, I think, from NASA. So I don't know if they are visible, but from satellite, so there are something that's traces of internal waves that are noticeable from, so they say 20 internal wave packets to be seen, so it's, so this is another picture from NASA of internal waves. So this is South China Sea. It's another bunch of internal waves here in the South China. I guess they are, it's possible to observe them because the upper layer is usually of more transparent water, and from a satellite what's observed is not the surface wave, it's the internal waves that are much bigger. In the case that here, if the conditions are such that here the upper layer is more transparent. I guess that there are situations when the upper layer is not transparent, but since these are visible from the satellite, this means that they are very large structures. Okay, so in conclusion, so we have formulated this problem in a Hamiltonian and even in canonical Hamiltonian form. So we have obtained studied the linearization and dispersion relation, and weakly nonlinear system which produces KdV, and of course other scales and other nonlinear effects remain to be studied further in the future. And finally, I have to thank to the organizers, Professor Adrian Constantin, Professor Haller for this invitation, and to Erwin Schrödinger Institute for this and many other previous programs where I have participated. Okay, so thank you also very much for your attention.
How will the results change if I move you to 50 degrees instead of the equator?
So qualitatively, I think that it's not going to change much.
So it's the same?
The thing is,
Apply to the ACC.
okay, probably most of these results qualitatively will apply well into other things. The thing is that when we have these currents and rotational, they induce rotation in the flow. I mean, if we move further, now we can keep it like two-dimensional. If it's like this, it will stay like this. But if we go to another non-zero meridian, this thing cannot be kept in gamma and gamma 1, they cannot be kept constant. So they will they will introduce some rotation in the other direction. So the rotational is three-dimensional effect. So this, I think, is going to start to destroy the picture. But otherwise, I mean,
You also had Colloid's forces in the two momentum equations.
I think it's because the rotation vector points up to the North Pole.
so the equator is quite, the equator,
There's still components.
Yeah, it's the horizontal part of
the equator is quite special, but I mean, there will be a bit of a destruction of these constant gammas if they will start to, because they will introduce, but I mean, again, the Coriolis effect and the other things, I'd say they will complicate a bit this. But I mean, we see from these pictures that there are internal waves that are kind of nearly solitary waves that are stable structures, and so these are a bit far from the equator in South China Sea, and so qualitatively I wouldn't expect much of a difference if we are near to the equator in these things. For as far as the waves propagate in one direction, mostly. So they have said that they have seen solitons with the crest that is 200 meters long. It propagates for. So there are such stable structures.
Another problem might be the fact that you've ignored the meridional direction, because all of your images show significant propagation in the meridional direction of all the internal wave pictures from NASA, for instance.
Yeah.
And then, of course, the Coriolis force does affect
Yeah.
that direction too. So how do you extend or think about such things when...
Yeah, this will, of course, further complicate the problem that's already complicated enough, as you can see. Of course, this is, if you go from a purely mathematical point of view, I mean, there are many, of course, there are many features that are yet to be considered. As you asked about the shortwave, yeah, this was not our primary concern, but I mean, because the results that we have got is within this range, and probably there are other interesting phenomena related to the short waves, and it is just that our primary interest was on the long waves, and It's not.
So I think you have some decay conditions for the Dirichlet operator to work out, and this seems to impose that you've got solitary waves. So how about the periodic case?
Yeah, well, of course, the periodic case, it's not in the Schwarz class, of course, but I mean, we have just linear equations, and I guess with the linear equations we can look at the sine cosine solutions and can make, so to say, an exception. And when we concentrate on the solitary waves, I mean, all these are Dirichlet-Neumann, these are formal expressions. I mean, if they are convergent, if they are not convergent, this is a separate question altogether. I mean, I have seen papers, they are doing numerical methods how to work out so there are, of course.
Do you think that a weakly nonlinear theory for periodic waves is sort of in the sense of
Well, these are just sine and cosine periodic waves. They are not periodic, so they are not periodic boundary conditions, if you mean this, yeah. For periodic waves, yeah, there are, I mean, different technique for the Dirichlet-Neumann, different set of Dirichlet-Neumann operators. If you want class of functions that are periodic, the Dirichlet-Neumann operators, they will change appropriately, right? So these would involve Dirichlet-Neumann for the solitary case, yeah. So if you want to work with periodic functions, they are quite similar, but I mean, there are specifics, yeah.